Hello, I'm Seung-jae Jung from III Excel Lab. Today I'll be introducing the DreamScene paper, which was published at ECCV 2024. This paper presents a text-to-3D scene generation method based on 3D Gaussian splatting. The primary focus is on scene level generation using a technique called formation pattern sampling. Before diving into the presentation, it's important to have a basic understanding of 3D Gaussian splatting, diffusion model, score distillation sampling, as these concepts are fundamental to how DreamScene works. If you are not familiar with these topics, I highly recommend watching the seminar titled 3D Gaussian Splatting for Real-Time Radiance Field Rendering and the seminar titled Text-to-3D Generation Using SDS versus ISM on this channel first. This will provide the necessary background to better follow this presentation. Text-to-3D scene generation is the task of converting textual descriptions into 3D scene. Existing methods can be broadly categorized into inpainting-based approaches and combination-based approaches. Inpainting-based methods such as text-to-room and text-to-nerve iteratively complete 3D structures from partial observations. On the other hand, combination-based methods such as set the scene and glass 3D integrate multiple models to refine object placement and scene composition. However, existing methods face several limitations. First, the generation process is often inefficient, leading to low-quality outputs and long completion times. Many models struggle to generate fine details effectively, resulting in blurry or unrealistic scenes. Second, multi-view inconsistency remains a major issue. Since many approaches rely on 2D supervision, the generated 3D structures often appear correct from certain viewpoints, but exhibit distortions when viewed from different angles. Finally, editing flexibility is limited. Most methods do not separate objects from the background, making it difficult to adjust positions, scales, or styles of individual elements. This lack of control restricts scene customization and adaptability. These challenges highlight the need for a more effective approach to high-quality, consistent, and editable 3D scene generation. DreamScene is a novel text-to-3D framework based on 3D Gaussian splatting to overcome these challenges. It introduces two key strategies. First, it uses formation pattern sampling, which enhances object generation through multi-time step sampling, reconstructive generation, and 3D Gaussian filtering. This method helps create high-quality objects with fine details, while reducing memory usage caused by unnecessary 3D Gaussians. Second, it employs a camera sampling strategy, which is used for environment generation to ensure 3D consistency. By structuring the camera sampling process in 3 stages, DreamScene gradually optimizes surroundings, ground, and full scene, allowing for a fully coherent scene. Additionally, DreamScene enables more precise scene editing by integrating objects and environments separately, making it easier to modify specific elements of a scene. DreamScene follows a structured pipeline. The process consists of 3 main stages. Please follow along with the pipeline figure as I explain each step. First, scene text decomposition. A large language model decomposes the input scene description into detailed object and environment descriptions. This ensures that objects and environments are generated separately, allowing for better scene composition. Second, object generation. Each object is optimized by a pre-trained stable diffusion model. In this stage, a formation pattern sampling technique are used during optimization process, helping to refine object details and maintain structural consistency. Third, environment generation. The ground and surroundings are optimized separately from objects to ensure scene consistency. Objects are then placed within the environment according to layout information, ensuring proper alignment with the ground and surroundings. In this stage, a three-stage camera sampling strategy is applied to progressively refine the scene, focusing first on the surroundings, then the ground, and finally integrating all elements into a coherent 3D composition. The first step in the pipeline is scene text decomposition. Given a scene description like an autumn park, GPT-4 decomposes it into detailed object prompts and a single environment prompt. For example, the object prompts might be a DSLR photo of a wooden park bench or a DSLR photo of a colorful playground slide. And the environment prompt could be a DSLR photo of an autumn park with fallen leaves and a paved walkway. This environment prompt is then used to generate both the ground and surroundings. The second step in the pipeline is object generation, where high-quality 3D objects are created based on the object text prompt. First, a text-to-3D point cloud generation model called point E is used to initialize the object shape as a point cloud. Then, each point is assigned a 3D Gaussian, forming the initial 3D Gaussian model. Next, this 3D Gaussian model is rendered from multiple viewpoints using 3D Gaussian splatting. The rendered images, along with the object's text prompts, are then fed into the diffusion model. To optimize the 3D Gaussians, the model predicts noise from the diffusion model in two different cases. First, it takes only the rendered images as input and predicts the noise. Then, it takes both the rendered images and object text prompts as input and predicts the noise. The difference between these two noise predictions is used as the loss function following classifier score distillation (CSD) method, a variant of the well-known score distillation sampling (SDS). By iteratively minimizing this loss, the 3D Gaussian parameters are optimized, refining both the shape and texture of the object to match the given text description. However, a key issue with CSD and SDS is that they rely on single-step optimization, meaning that at each iteration, it updates the 3D model based on only one time step of noise prediction. This often results in unstable geometry and poor surface details. To address this, DreamScene introduces formation pattern sampling, a technique designed to enhance object generation through three key components. First, multi-timestep sampling improves stability by sampling multiple timesteps per iteration instead of relying on a single-step update. This approach allows the model to capture detailed and realistic surface information at early timesteps, such as 200 to 400, while capturing rich semantic information at later timesteps, such as 600 to 800. Second, reconstructive generation enhances object textures after the optimization through multi-timestep sampling. To further refine details, DreamScene leverages DDIM-based pseudo-GT images derived from Lucid Dreamer model, which capture plausible textures from small timestep denoising. By comparing these pseudo-GT images with the rendered images of the optimized object using an L2 reconstruction loss, DreamScene improves texture accuracy while preserving shape consistency. Third, 3D Gaussian filtering is applied to remove excessive or redundant 3D Gaussians. To determine which Gaussians should be pruned, DreamScene calculates a score based on two factors. First, Gaussians that are closer to the rendering plane have a stronger influence on the final image, so they are given more importance. Second, larger Gaussians contribute more to the rendered scene. Using this score, DreamScene gradually removes unnecessary Gaussians throughout the optimization process, ensuring that only the essential Gaussians remain to accurately represent the scene. The third stage in DreamScene's pipeline is environment generation. Environmental elements are optimized separately from objects. The environment is initialized differently for indoor and outdoor scene. For indoor scene, cuboid-shaped 3D Gaussians are used to form walls, floors, and ceilings. For outdoor scenes, hemispherical 3D Gaussian represent open landscapes like the sky and distant surroundings. After initialization, objects are positioned according to the layout information with a fine transform. DreamScene applies a three-stage camera sampling strategy for environment optimization. Before diving into the three stages, it is important to note that this process freezes the parameters of the optimized 3D Gaussian objects and only updates the parameters of the environment Gaussians. First, the surroundings are optimized by sampling cameras near the center of the scene, focusing on refining walls or distance backgrounds. Second, the ground is refined using structured camera placements. For indoor scenes, cameras are positioned to cover key object placement areas and flow regions. For outdoor scenes, cameras follow a radial pattern, capturing views from different distances to ensure even ground coverages. Finally, all previous camera views are used together to refine both the ground and surroundings. This ensures that the ground, surroundings, and objects integrate properly while maintaining full scene consistency. Here are the results of indoor scene generation. The model successfully constructs structured environments with detailed objects such as furniture and decorations. The generated walls, floors, and ceilings maintain spatial consistency. These are the results of outdoor scene generation. The model effectively captures open landscapes including natural elements like trees, grass, and distant surroundings. The scene maintains coherence across different viewpoints, producing a visually consistent outdoor environment. This slide compares DreamScene with existing text-to-3D scene generation methods. In the first row, which shows the training views, all methods appear to generate plausible scenes. However, in the second row, which presents random views, existing methods fail to maintain structural consistency. In contrast, DreamScene preserves multi-view consistency, ensuring that the scene remains coherent and visually accurate from all viewpoints. Finally, this slide demonstrates DreamScene's scene editing capabilities. The first four images show object-level modification, including adding a person, removing furniture, and repositioning objects. The last three images showcase style editing, where the scene is transformed into cyberpunk, Minecraft, and UQ styles. In summary, DreamScene introduced a novel text-to-3D scene generation framework addressing limitations in quality, consistency, and editing flexibility. By leveraging formation pattern sampling and a structured camera sampling strategy, it achieves high-fidelity, coherent, and editable 3D scenes. Despite its advancements, DreamScene has several limitations. First, as shown in the ablation stud figure, applying only multi-time step sampling already yields results comparable to the full formation pattern sampling. While Gaussian filtering improves memory efficiency by removing unnecessary Gaussians, it tends to preserve only larger surface Gaussians, failing to capture high frequency and realistic details intended in original Gaussian splatting. Additionally, DreamScene still requires separate optimization for 3D Gaussian objects and environment Gaussians. This results in long processing times similar to previous methods. Thank you for watching.